Hello, my name is LBarnes. I'm a junior studying computer engineering and I'm enrolled in 332 and 312. I am not enrolled in 342, so I will not be talking about the EMAG perspective. I will be talking about the reception of radio signals in linear systems and microelectronic perspectives of this device. I will be walking through each step and giving details on each component of the device. When we receive the signal on the antenna will also pick up on other surrounding signals that we do not want. What we must do is use a bandpass filter to differentiate our signal from the surrounding signals. If we are making this reception device for a certain cell phone company, we will know exactly what frequency to expect our signal to be in. We can tune the bandpass filter to where our signal is, and all other signals will be attenuated. The signal will be attenuated some from traveling across large distances through the air and obstacles. We will need a low noise amplifier to amplify our signal to an amplitude that will be easier to work with. This amplifier will also have less noise than a traditional amplifier. After our signal is amplified, we must put it through the mixer. The mixer is a device that multiplies the signal by a carrier frequency, such that the product signal is unique and can be differentiated from nearby signals. Every time you are listening to a radio and change the channel, you are selecting a different carrier frequency so you can pick out a specific signal from the rest of the radio stations. When the audio signal is mixed with the carrier frequency of omega naught, the audio signal has a very large frequency shift by omega naught. The result is that two copies of the audio signal are now located in the positive omega naught and the negative omega naught. Now when the signal is transmitted, only radios with specific bandpass filter can receive the signal. The actual mixing process will vary from the type of radio wave you want, whether it be frequency modulation, amplitude modulation, or phase modulation. The mixer contains what is called a local oscillator in order to produce the carrier frequency. The local oscillator uses something called an LC tank, which is a loop containing a capacitor and an inductor. A property of the capacitor is that it allows current across it immediately, but resists the change in voltage. The inductor allows an immediate change in voltage, but resists the change in current. If a power is applied to these two elements while they are connected, they will each take turns holding their respective fields and converting back and forth from electric field and magnetic field. The current across the capacitor will oscillate at the resonant frequency of the LC circuit. Because the LC loop is mostly reactive, the power loss to produce the signal is small. However, the inductor can have a small resistance that consumes power, so the loop has a constant power supply. We do this by having two amplifiers feeding into the gate such that every time the local oscillator falls below its max amplitude, it gives it the boost that it needs to remain constant. This AC voltage is then multiplied to the audio signal using a transformer. The product is our fully mixed signal. After mixing, our signal will be amplified again by a regular amplifier. To amplify the signal, we will use a common source amplifier. The amplifier is carefully designed such that the gain is big enough to produce a usable signal, and that the swing is good enough so that our VN can have a large range of amplitudes before throwing the amplifier out of saturation. One of the most important components of our common source amplifier is our load. We need a big output resistance such that when we produce a large current from the amplifying transistor, we can have a large voltage drop at Vout. The best load with the best output resistance we can have is a current source. The current source will be a current mirror. The current mirror is a circuit with two transistors with their gates connected such that the current flowing on one side will be mirrored on the other side. This allows us to have a large change conductance and a large output resistance, which is key for having a large gain. After our amplification, we will have a low-pass filter. The reason we need a low-pass filter is because in order to mix our signal, we multiply it by a cosine wave. This produces extra copies at higher frequencies that will not be needed. The low-noise amplifier can do this for us. At the very end, our signal will be converted back to its original state. It is back to an audio signal and can go back through the analog to digital converter to either be played or stored into memory in a digital format. This concludes the reception portion of a radio system. Thank you.